Okay, good morning. So, yeah, finally, we come to the last class for the lecture, for the whole lecture. So, today we are going to focus on the thermal actuators, okay? So, I think some of you have chosen like an actuator as your final project. The actuator can be a translational, linear actuator, or either rotational actuator. No matter what kind of they are, in the final project, I really want you to design the actuator much better than the actuator I have introduced in my classes, okay? So not easy. So they need either to be have a long travel distance or need to have a very large force or the combination, okay? So today I will introduce another actuator. This actuator can give you a large force, but unfortunately, the traveling distance is very, very short. So we will try to see how to do, okay? Try to introduce different methods. Try to combine the large force and also the long distance travel at the same time, okay? So talk about thermal actuators. Actually, we want to look into the fundamentals first. So the fundamentals are, when you look into the diagram of a piece of a rod, these kind of rectangle structures. So when we heat up these kind of structures, so this structure will extend on 3 different dimensions from x-axis, y-axis, and also z-axis. So the whole structure will be expanded, okay? This phenomenon is coming from any kind of a material. They also have we call the very special property is like a thermal expansion. Okay, so how large the structure can extend during the heating up or cooling down contraction depends on a parameter we call the CTE, coefficient of thermal expansion. Yeah, so coefficient of thermal expansion means the degree. Okay, how to measure the degree? Okay, of the expansion or contraction of a material during the temperature change. Okay. So the definition of CTE is equal to the equation over here. So that means over some kind of temperature differences, what kind of length change in this material and corresponding to the original length. Okay, so that's a definition. So CTE for most of the material is approximately constant. Okay, for a quite larger, quite larger of the temperature variation region. Actually, if you consider the whole temperature range, it's really not a linear coefficient or constant coefficient because approximately. So that's why we usually use CTE as a one number, okay, instead of an equation. But if you want to do it accurately, many times we will consider it's a become equation, either not only a one spot point, okay? So that's CTEs. And usually the CTEs increase with the increment of temperature, okay? We increase the temperature, the CTE usually increase. But for easy calculation, usually we'll use a one single, point, one single value for calculation. And the second one, for homogeneous and isentropic material, the coefficient apply to all dimensions. So homogeneous means the material itself is no differences on the ingredients everywhere. It's called homogeneous. Isentropic means there is no directional preference for the material property. Okay, for example, like for concrete. Okay, you have concrete. Mix everything together, sand and also concrete together to form the final structure. The concrete can be considered is not directional material. You go every direction has a similar material property. However, if you put a steel inside the concrete to form a whole structure, so the structure will have some kind of difference in along the steel direction. Okay, so that means the material become not isentropic. It becomes directional. Some direction has a very strong, material property, but the other side, on the other direction, there's not such a strong material property. So let's pick called anisotropic. So currently we consider only homogeneous and isotropic material. That means the material ingredients everywhere is the same. And also there's no directional of the material property. So there's a homogeneous and isotropic material. So the coefficient, in this case, the CTE can be applied to all the dimensions. That means when you have an expansion on x-axis, the same degree of expansion will happen on the y and also z direction. Okay? So they have a similar property on different direction because there is no direction, no situation, and also it's homogeneous material. It's no differences on the gradient. Here I give you some of the CTEs for some materials which has been used a lot in the math application. Okay, so it's a table over here. So it's a very useful table. So we look into the table, and we can group these different kind of materials into 3 different groups. The first group we can look into the ceramic-related material. For example, like a silicon dioxide, silicon nitride, glass, fused quartz glass. It's glass and the silicon. Silicon is over here. Okay. Yeah, it's distributed randomly. Okay, so we look into the first category. For example, like silicon, the CTE is only 2.6 times 10 times minus 6. Okay, we just mentioned the first digit. Okay, 2.6. So it's pretty low actually. Okay, and when you look into quartz, it's even lower, 0.27. So it's 1 order magnitude lower in the CTE than the silicon. Okay, and also glass. Either different glasses are Pyrex or regular glass. They also are under 10. Okay, I mean the CTE under 10. So this is the first category. So for ceramic material, you can see the CTE is usually very low. That means when you heat it up, the ceramic material, they don't expand too much. Okay? Yeah, so at the same, yeah, so vice versa. So if you lower down the temperature, they don't contract very much. Okay, so this for ceramic material. The second category we can look into like a metal. Okay, for example, aluminum, gold, like iron, lead. Okay, so first we look into aluminum. Aluminum has a CTE is 25. So compared to silicon, it's about 10 times, much more. Okay, it's 10 times. And also you can look into other materials, metal materials like brass, like cadmium. The chromium is very special, okay, and also copper, okay, and gold. So indium, iron, lead, nickel. So most of them are between 10 to 30. Yeah, it's about like roughly 1 order magnitude higher than ceramic material, roughly, in average. So metal has the median thermal expansion coefficient compared to other material. So this is a second category. The first is a ceramic, second metal. The third one, we will consider like a polymer material. Polymer material, for example, like polycarbonate, polyethylene, okay, these two. Polycarbonate is ABS, so you can see the alpha is 70. And also on the extreme, the polyethylene is 200 something. So for polymer material, you can see the thermal expansion coefficient is even higher than the metal. So roughly around like 1 order magnitude higher than metal. So you can consider ceramic is the lowest one, it's below 10. Metal is around 10 to 30. And for polymer, sometimes above 100, even to 200. Okay? So when you want to design the thermal actuator, you need to consider the thermal expansion coefficient because that means how much deformation you can have when you input the thermal power. Okay, finally. Because at the end of a project, we want to consider if we want to have a large distance movement. So what kind of material you want to choose is also important because in the final project, I did not define any kind of material for you. You can choose by yourself, okay? So it's important to understand the material property first, okay? So if you use ceramic to do the job, it looks not very good for long distance extension. But in terms of a force, they can give a lot of force. But in terms of displacement, they won't give a large displacement. And also for the course, and the fused course, I think it's the lowest thermal expansion coefficient material in the world. Okay, so you can see the thermal expansion coefficient is very, very low, 0.27. Okay, so almost does not change with the temperature variation. So that's why we usually use course as some kind of a frequency, the timer, using course as a timer material. Okay, we knock on the course some kind of force, so the course will vibrate in certain kind of frequency. That frequency does not change with temperature variation. Yeah, so we use that a lot in our watch, in computer. Okay, so it's a good material for timer, but course is definitely not a good material for actuator. You won't give you any displacement, even you have a large temperature variation. Okay, so this is a material-wise consideration for the actuator. So now we consider the next topic about the strength. So when we have thermal expansion, not only the structure expand, okay, become longer, become wider. Also, if you clamp the material inside between two structure, for example, like two walls, so the material will give a strong strength onto the wall. Strength times area means a force, okay? So the strength caused by the thermal expansion will be expressed by this equation. So the thermal expansion strength, okay? The strength original, the definition is delta L over L. The displacement over the original length. That's the original definition. But from the thermal expansion coefficient definition above, so this part will be the strength. So you leave the delta T into the other side. So alpha delta T equal to the strength. So that will be the thermal expansion coefficient. Thermal expansion caused the strength, okay, in the temperature elevation case. Okay, so when we put this kind of material clamp inside the wall, so when we heat up the material between, so we will find out if the wall is a solid wall, rigid wall, will never deform. Okay, so in this case, a very strong stress will be generated along this direction. So the stress generated will be expressed by sigma here. So the total force from the thermal expansion will be the area times the stress, A times sigma. And the sigma equal to Young's modulus times the thermal expansion caused the strength. Okay? The strength actually is very small. We'll take a look at it later on. But here we will times a very strong, Young's modulus, depends on the material. If you have a very high Young's modulus material here, even though the epsilon is small, after times the large Young's modulus, you got a large force here. So we will see later on. So finally, the epsilon will be equal to alpha delta T, depends on the temperature elevation, and also your CTE, your coefficient of thermal expansion. Okay, so from this equation, you don't have any filling because you have not plugged into any kind of parameters and also the real values. So now we consider one case. The one case for silicon beam, because we are doing bulk machining, surface machining silicon substrate. So we will first consider if we use silicon as a material, what will happen? Okay. So in the future, you are not going to use only silicon. You can try to use different material. Okay, as I mentioned earlier, metal or polymer. Okay, so for silicon, the alpha is quite small, 2.6. So now we want to consider to design a beam with a length of 100 micron. The width and thickness is 10 micron. It's a pretty small beam. Okay. So now we plug into those conditions, and also we want to elevate temperature for 100 degrees C, from room temperature to 125 maybe, okay, degrees C. And then plug in the Young's modulus here for silicon. And also we consider also the thermal capacitance, okay, of the beam. Okay, so you can have some kind of reference book which can give you this kind of value. So end out, we found out the force generally by this kind of temperature elevation will become 2.6 millinewton. Consider millinewton range of the force is like a 3 orders of magnitude higher than we had in the electrostatic actuator, right? We consider the count drive. The count drive, can you remember the force which can be generated by the count drive actuator? It's in only micronewton range. But the thermal actuator here, only one single beam, very short beam, can give very large force in the millinewton range. Okay, it's 1,000 times higher than what we can do on the electrostatic actuator. But at the same time, when you look into the other side, that's about the displacement. The displacement is only delta L is only equal to 26 nanometer. It's quite small. Okay, so this gives you an impression. So thermal actuator can provide a very large force easily. Okay, because the thermal strength, even though it's small, because we have a strong Young's modulus over here. So when you times the two together, you got a very strong force over there. So large force, however, the displacement is not that much. Actually, it depends on the material. Currently, we are using silicon. So you got this final results of 26 nanometer. If you are using ABS, the polycarbonate, well, polycarbonate has like 100 times of the CTE than silicon. So displacement will become 2.6, yeah, easily. However, the Young's modulus of polycarbonate is like 1,000 times smaller than silicon. So in this case, you won't get that much force. So if you change material, you will trade off between the force and displacement at the same time. You reduce the force, but increase the displacement. But the total energy actually will be similar, total energy. So talking about energy, then we take a look what kind of energy efficiency we are using for the thermal actuator. So for the input energy, okay, so currently we heat up the whole substrate by 100 degrees C. So the thermal capacitance of the material is just we mentioned earlier. So we have these two times together, we got the input energy will become like a 700 picojoule. It looks not very much, right? It's picojoule range. However, when we look on the other side, what kind of output energy, the work we are doing by using this actuator. So we consider the work. So the work will be defined by the force times the displacement, okay? They integrate from the beginning to the end, okay? So in out, you got a 26.45 picojoule, the output work you have done throughout the whole process, the extension process of the actuator. So you end out, you find the efficiency is pretty low, only 3.7%. Remember, last week we talked about the electrostatic actuator. What kind of the efficiency we got? Can you remember? I think it's better to come back to take a look, okay? Yeah, so this is the electrostatic actuator last week we talked about. So the efficiency is easily 50%. 50%. It's pretty high. Okay, the only 50% loss is because we want to charge the capacitor. So during the charging, you push the charge onto the capacitor. There will be some heat loss along the connection electrodes when you're doing the charging. So that's the only loss for the electrostatic actuator. So it's quite efficient for electrostatic actuator. However, the force is not that large. The output force, let's come back to see the output force. The force is only 1.55 micronewton. Okay? So now we have a 2.6 millinewton easily. The displacement is larger, it's around like 1 micron. Compared to the thermal actuator, it's only like 26 nanometer. It's pretty small. Okay? So if we compare these two, on the back, okay. So we compare these two. So we have an image about okay, it's here. Okay, we have a large force, small displacement, and very low efficiency. Okay, for thermal actuator. So you want to give the large force, I think it's definitely a good choice by using thermal actuator. But if you consider want to have a high efficiency, it may not be the good one. Okay, because it loses a lot of energy into heating up the material. Okay, heating up the material takes a lot of energy actually. Okay, so that's the first compression. So now we need to consider how to balance between the force and also the displacement we can have. Okay, so there are several ways we can enlarge the displacement, but at the same time, you need to reduce the force as a penalty. So it's a trade-off. The total power, you times the displacement and also the force, that will be the total power, the work you are doing. So they will be similar, actually. The total power, because the power, you input the total power is a fixed number. So the total power needs to be divided by the extension, the displacement, and also the force. So if you put too much on the force, you get much less on displacement. You put much on the displacement, you got a small force. Okay, it's vice versa. So now we consider the first one. We can use a leverage method. Leverage method, for example, like extending beam, extending arm, the design. So you have a long arm over here. Okay, so you fix one end, and then put the actuator on the other side. So the supporting point is at the end here, and we push the long arm by using the actuator here, by heating up the actuator here. So when we're heating up the actuator, they will give a small displacement to push the beam a little bit forward. However, because of leverage effect, we have a small arm over here, but large arm on the end, at the end. So at the end, the displacement will be enlarged by the factor of large x over small x over here. 这是杠杆原理. Okay, it's a leverage. So for example, if you design a large x as 10 times of a small x, in this case, you can increase the displacement by 10 times. However, the force over here and the force over here will be reduced by 10 times at the same time. So you reduce the force, but try to increase the displacement at the end. That's an easy way to trade off between these two by using some kind of mechanism, the leverage mechanism to do the job. Okay?